I'm going to walk you through a really significant application of derivatives, and it's the optimization example. The specific optimization example I'm going to walk you through is the volume of an open top box. Now, back in pre-calculus or even in algebra, we could use a parabola and find its vertex, and that vertex would give us an optimal point, an x and f of x that were the highest or the lowest. But that could only carry us so far. When we get to calculus, we find that when the derivative of a function is equal to 0, when the derivative is 0, we get an optimal value. So let me write that just to make sure everyone's understanding what I'm saying. When the derivative is 0, or maybe I should say the x for which the derivative is 0, we get the maximum or minimum. In other words, we optimize. We get the maximum and minimum values of the function. How do you find the maximum or minimum? So if we're talking about maximizing, optimizing, minimizing, etc., we find the derivative, and after you have the derivative, set it to 0, and then that will lead us to finding the x's that give us that derivative of 0. Here's a real standard example, and I'd encourage you, if you don't already feel really comfortable with this one, get to the point where this example feels really, really easy to you. Let me try and make it a little bit bigger here. Here's the example. A box with an open top is to be constructed from a rectangular piece of cardboard with dimensions B by A by cutting out squares of size X at each corner and then folding up the sides as in this figure. So far, what this example is asking us to do is just express the volume as a function of X. Let's make sure we understand what's going on here. Can you picture this rectangular, cardboard? You know, maybe you had cereal in your home and you took the cereal box and cut off the front of the cereal box. Yeah, you want to open up a craft business making bowls or dishes out of reused product. Cut the front of your cereal box out. Can you picture it maybe looking like this? And what would happen is, if I cut these squares out, now they do need to be squares, and they have to all be the same size. If I cut these 4 squares, then can you picture how I could get this box? It doesn't have a lid, but can you picture how I could get this box? If you have a jewelry business, you want to sell some jewelry, you could so easily make small jewelry boxes this way. I've made boxes like this out of Christmas cards. It's a nice way to reuse some of those nicer cards. But the way you do this is you cut squares in the 4 corners of the rectangle, and then here's the fold lines. We fold here, 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 and here. And now the bottom of the box, this part here, is this. And then here's the sides. So here's the longer sides of the box are these 2 pieces, and the short side of the box will be these 2 pieces. These squares that we cut are not part of the box, right? These are gone now. They've been cut off. They're no longer part of our box. I hope that general idea of what we're doing in this problem makes a little bit of sense. So let's see how we'd approach this. When we pull those sides up, we can see that the height of the box is going to be X. Any of the X's, because our squares are all the same, right? But that's how tall that box is. So the height will be X. We could see the width of the box is this amount here. These are all 4 equal, right? So that green line is the width. 1, 2, use any of these 4. They're all the same, right? And how long is that? Well, if it started out to be B units long, and we then subtracted 2 x's, then what we've got left is the B minus 2x. And we could call this the width of the box. The width is going to equal B minus 2 x's. And we can find the height, or I'm sorry, the length, real similarly. The length is going to be the length of A minus 2 x's. Do you see that? Let me draw it here. We'd have that this length A, or not A, the length is the full length across A minus each of these 2 x's. So A minus 2x. There's our dimensions. One more time, let me just document them here. Height is X. Width is B minus 2x. And length is A minus 2x. So now I can write the volume. Volume of a rectangular prism or a rectangular box is length times width times height. Doesn't matter what order I put those in. I'm going to try this. When I write it out, I'm going to do 8, the height, and then the width, and then the length. So the volume with respect to X will be the height, X, times the width, B minus 2x, times the length, A minus 2x. And there you have it. Now, if I wanted to find the optimal volume, if I took this to the next level, said, well, now that I've expressed the volume as a function of x, let's find what size would the x be so as to maximize the volume of this box. Then what I'm going to do next is I'm going to find the derivative of the volume. I'm going to stop here and say that to do that we could distribute the x and then use some FOIL and expand this to get a third degree polynomial. After we had that expanded, we would just have a polynomial, and we could find the derivative of that polynomial using the power rule. But try that a few times. Try some specific examples where you're given a number value for A and B, and see if you can't find a process that works for you to find that volume, the optimized volume, and then to find the value of X that gives you that optimal volume. Well, I hope this short video has helped you get started with this type of an optimization problem. Feel free to reach out to me if you need a little bit more assistance with that.